Okay. So as you guys all know, we're going over interrupts today. Now, to kind of start off, I'm going to ask the class about your ideas of what an interrupt is. You guys gone over multiple classes that went over it. You went over an OS, an operating systems course. You went over in 127 effectively. Can anyone tell me what the purpose of an interrupt is?
So that way the CPU doesn't have to wait or like hold for something to be finished. It can do more useful work. And while it's waiting, the interrupt being processed, and when it's ready, it will send the interrupt to the CPU, and it'll come back to it.
Yes, very good. That's effectively what an interrupt is. It is a system that allows basically signals to come into the processor that don't have to be waited for. The processor doesn't need to take up time to look for all of them. It can just occur, and then the operating system can interrupt itself. I'm sorry, the CPU can interrupt itself, move to interrupt service routine, run that routine, and go back to its normal operation. It allows the CPU to be far more flexible than if you just had to pull each time you want to look for a signal. Especially since there might be a case where you're doing some bit of work, and that signal didn't come in, or you didn't check it at the time which the signal came in. The interrupt alerts the processor with a kind of like a high priority condition, which will usually tell the processor to switch to another executing section of code. We call those interrupt service routines. And along with that, there are also different types of interrupts. Now, since you guys have learned about interrupts in other classes, can you guys tell me what the different types of interrupts are? Raise your hand. Sure.
Software and hardware?
There are software and hardware interrupts, that is correct. What do we usually call software interrupts?
Traps.
Traps, yes. What do we usually call, well, what are usually hardware interrupts called? Yeah, pretty much just interrupts. Yeah, you have a different name for software interrupts, but for hardware interrupts, you call them interrupts. What other types of interrupt conditions can we look for when it comes to a microcontroller?
Oh, because I was going to say non-maskable interrupts, but yeah.
Actually, that's another area, so that's going deeper into types of hardware interrupts. What's the other type of interrupt in that same area? You said, which ones did you just said?
Non-maskable.
What's the other one?
Oh,
Maskable. It's maskable, yeah. So you can have non-maskable interrupts, you can also have maskable interrupts. Do you guys know what's the difference between a maskable and a non-maskable interrupt is?
Maskable interrupts are usually used for power failures or anything that you can't. Sorry.
Yeah, I think so.
Wait,
Non-maskable means you can't turn it off.
Yes.
Yeah.
Yep.
Yeah.
And that's for crucial.
So power failure.
Power failure is one of the situations which you would need, you would want to use for non-maskable interrupts. You want your power system to say, hey, something's failing here. Pull a pin low or pull a pin high, whichever one is simpler for your system to do, and that should then tell the CPU to do an operation before it either failure occurs or try to save itself, basically. What about maskable interrupts? Peripherals, yeah. So basically, when you have a maskable interrupt, that's usually a case where, let's say you have some peripherals that are doing their thing, and one of them's going to give you an interrupt, but you're already servicing one at a time. You can mask those interrupts, say, okay, I don't want to listen to you guys right now, I want to disable interrupts. Then you can do your interrupt service routine, and then you can enable interrupts again, and then you can move over and do the other interrupts that need to be serviced. As long as your system has some way of storing the information about which interrupts have occurred, and don't just let them go once the signal's gone, you can go back and check the interrupt registers to actually run those service routines. Typically, your CPU will do that for you. So that would be maskable interrupts. Now, in terms of hardware now, so we can get to it, we still haven't gotten there. What are some ways that we can, what are some type of, how should I say this? It's a type of interrupt, but it's a type of interrupt signal. So we have two types of interrupt signals. Do you guys know what those are?
Strobe, asynchronous, asynchronous.
You can have asynchronous and synchronous interrupts, but from our point of view, it doesn't matter too much. What did you say?
Strobe.
Yeah, we can have a strobe. So effectively, like an edge-triggered interrupt, or just a single pulse. There's also yes.
So strobe interrupt is a edge-triggered interrupt.
You can yes.
Okay.
There are some actually interrupts that look just for the pulse to occur, and once it goes high and then back low, then they'll occur. But typically, a lot of devices look for, it's a particular word I'm looking for actually. And you did this a lot in 125, you did this a lot in 124. It's a way to trigger, yes, level sensitive is one of them. What's the other one?
Level insensitive?
No, we're sensitive to all things here. No, yes. Edge triggered, yes, that's what I'm looking for. So we have edge triggered interrupts and we have level triggered interrupts. Is there any ambiguity to that? Is anyone in here who doesn't really understand
what's
this?
the difference?
Okay. So
Oh, so level would be like, if at any time if I check the status of this, if it's at this level, then it's considered an interrupt.
That is
Whereas
correct.
on the edge, if it's just edge triggered, the instant that it happens, then it's, that causes the interrupt.
exactly. So let's say you have, like for example, the reset pin on your SJ1 board. The reset pin is actually level triggered. So when you pull the line low, it's not looking for a falling edge, it's just looking for the fact that the edge, the actual signal is low. Once it's low, because the reset pin is active low, it will trigger and go into the, actually kind of holds inside the reset, inside this reset loop. Once it goes back high, that's when it will begin to reboot. Yes.
But wouldn't level sensitive then effectively be a synchronous interrupt? Because like if that interrupt doesn't stay that level, when the CPU reads for it, then it's not going to be caught as an interrupt, or that signal's not going to be caught in time.
So it depends
if
on.
if it's not at that level during that state when the CPU reads for that level, then the CPU won't ever know that it happened.
Yes, actually, so actually before I even go any further, have you guys gone over interrupts inside of the 146 lecture?
Yeah.
Example?
Yes.
Cool, you guys have gone over that. Okay. So you guys, you know about the state machine within the Intel 8086 and has the state for when it checks that stuff. A lot of systems will usually have hardware that's specified, like besides having it integrated into the state machine, it'll have hardware that will just interrupt the state machine and put it over to another spot. And typically the state machine is so quick that in the time in which it checks again, you can call it synchronous, but for the most part, there's a little bit of hardware that stores that information for you, and then is waiting for that state to hit, because it's always going to hit every single time you loop, and then tells the CPU, hey, just so you know, reset just happened. So quit what you're doing, do the reset routine. Yeah. If you talk about it synchronously outside, you could say that it's synchronous in terms of some clock. Therefore, if you had some way of checking with every clock cycle, you can consider that synchronous. Otherwise, the other way would be a polling. You'd always check it every so often. So synchronous is usually synchronous to some clock external to the device, but they're usually the same clock across both devices. Okay. Okay, so here's another one for you guys. What is an ISR? What does it stand for?
Interrupt service routine.
Very good. Now explain, what is an ISR? Like, what do ISRs do? Why do we make them? Why is that even a term?
A series of instructions that the CPU follows when an interrupt is triggered. So, yeah.
Precisely. All right, so you guys, so you guys have gone a lot through this inside of 146. So I need to go. I don't need to spend
No,
any
we
more
got
time.
it from 127.
That's also true. Yeah. I just said 126. I meant to say 146. Yeah. All right. So what things can create an interrupt for your microcontroller?
Keyboard, or like any kind of.
Yeah, button press.
Microcontroller.
Oh,
And also
right.
raise your hands this time because I want to see if I can get people who haven't already spoken. So the people in that edge over there. What can cause an interrupt?
Come on, guys.
Have you guys taken 142? You guys on this material 127? I mean, like, you kind of went over it.
There's interrupt code. Copy paste it.
You guys know?
Sort of error.
This is all new material. No guesses? You guys can give guesses, like, it's not a problem. Please, someone raise their hand, give me a guess.
No, I was making that stage one.
Yeah, I'm not gonna attack you.
I'm not gonna tell you to change your lifestyle, you know. Or
So yeah, so what things, so we've been working with the LPC 1756 this entire time. I'm pretty sure you guys saw this when you guys were looking at the data sheet, right? You guys were looking at the data sheet, correct? So I'm pretty sure one of the steps it talks about enabling interrupts, what can create an interrupt? Yeah.
Well, won't the interrupt occur when the program sends a signal indicating to CPU that the do load an interrupt?
That'll be more like a software interrupt. We're looking more for hardware interrupts. Yeah. Yes.
Power failure?
Power failure modes? Sure, but what? Let's think more on the LPC 7056. More on the peripherals, not less on the NMI side. Come on, guys. What are the last labs that we did? Okay. Could a interrupt come from UART? Okay. What other devices could they come from? What other labs did we do? Well, hold on, I'm gonna take some okay. Right, so we had GPIO, and then what other one? Was there any instance of any, like, in the steps Joe did follow and that had anything to do with interrupts? Yeah, no, that would be what type of interrupts? If you're switching, if you have a switch changing. It would be, but like for what particular peripheral in the LPC? Come on, guys, any of you guys know this? When you're working with the switch, what peripheral did you talk with? Did you communicate with? Okay, so if that's peripheral you talked with in order to get the switch to work, and it also gives you interrupts, then what peripheral would switches be under? There you go, reference. So we had a switch, and you used the GPIO peripheral to work with it to either read from it. If you have an interrupt that had to do with the switch, which peripheral would be under? Anyone else know that? No, hold up. What did you say? Say that loud.
I'm just saying, I think it would just be GPIO.
It is GPIO. That's it.
Oh.
Yeah. It would be a GPIO interrupt. It'd be a pin interrupt. So in that case, when you press the button, if it was set up sufficiently, you could have it trigger on a falling edge. So let's say when you press the button, before you press the button, it was high. Press the button, that level shifts low. And at that point, you'd have a falling edge interrupt. You can set those up, and that's actually what your lab for that tweak's going to be about. You can also do it for rising edges. You can, actually I haven't checked to see if you can do level. I'm pretty sure you can do level. I'm not sure, because I've always done mine with falling and rising edges. Okay, so outside of the ones that we've done for lab, if you guys know of any other type of peripherals that can be used on the LPC, what are the other peripherals that we can use that have interrupts that can occur?
Ethernet.
Ethernet, yes. Any other ones? An analog interrupt? Yes, an analog ADC interrupt, yes.
I2C.
I2C. Anything else?
Quadrature encoder. Quadrature encoder.
Is there a module for quadrature? There might be actually in the PWM section. There might actually. So I'll have to check that. But that might actually be one of them. Here's another one. Here's like a really, this one's more internal to the device. You wouldn't. It typically you don't put any pins out, but you can. Has to do with, think of it kind of like a clock. There's another interrupt.
Okay.
Say again?
Okay.
Okay, I'll take that. The time interrupt. Usually have a set of timers inside of your LPC that can run. So, yeah, so usually have timers. And you can preset the frequency, and then every single time that timer, let's say elapses or rolls over and overflows back to 0, you can then have an ISR be emitted from that. There are I think there are 3 timers in the LPC, I could be wrong. And there's also another thing called the IRT, the repetitive interrupt timer, which will run a particular task at a particular time that you set for it. Similar to the other timer interrupts. But I forget why it was distinct. I used it for another project though. But yeah, basically almost all of the hardware peripherals have their own dedicated interrupt system. You'll notice that almost every single one you see, if you're not doing interrupts, you'd have to skip over the line that said, initialize interrupts for this particular peripheral. Okay. Now, since you guys have been going over interrupts in 146 lecture, Have you guys gone over nested interrupt vector tables or nested interrupts at all? You guys have?
Yeah.
He's nodding his head like, yeah, no, we've totally done
I
that.
think it was like a really small mention.
Okay.
Everyone's been asking questions that were prior to that topic, so.
Okay, no problem. So I'm just gonna go over it real quick. The picture I have up here is just a normal, let's say, kind of run-of-the-mill interrupt. Your system has no priority system. It doesn't have any bias towards one interrupt or another interrupt. And as it's running, you have your normal program processing through time. And then interrupt occurs. It then changes context, switches over to the other service routine, runs the interrupt. The interrupt then does a interrupt return, turns back to the program continues on its way, as you would normally see for most interrupts. And then we went over different types of interrupts, hardware, maskable, non-maskable. And then you have something like this, where you have a nested vector interrupt table. With nested interrupt table, with an NVIC system, which is usually what it'll go by, if you're looking for a microcontroller that you want to use in the future, and you want to use interrupts with that microcontroller, you might want to see if it has an NVIC system. Typically, you'll have your main running, and at some point, another interrupt will occur. It'll jump into, let's say, ISR1, run its service routine, but sometime in the middle of that, it might end up jumping into another interrupt that has a higher priority. So nested interrupt systems, interrupt controllers, typically have two things: priority and the ability to nest. So you can have multiple ISRs running within each other. So if we wanted to, somehow we could trick the system to run as many ISRs as possible, and after the first ISR is running, in the middle of it can be interrupted, another ISR will run, a higher priority one can interrupt that one, and just keep going up until you get to the end of your priority list. If you have an ISR of a lower priority, typically those ISRs, the information is stored so that when the higher priority ISR is finished, it can then move back and run the ISR that was there before. Let's assume that ISR 2 got ran first, and then in the middle of its running, ISR 1 occurred, like there was a interrupt flag that came up for that one. ISR 2 would continue to run, and then once it finishes, then the lower priority ones will be serviced. Similar to FreeRTOS. FreeRTOS is very similar to a interrupt system. And actually, back in the day, a lot of people just use interrupt priority systems, NVIC systems, to just do like the different tasks. You could set up, there's like usually a window of, you have a timer and you have like different tasks that you could run within that. You can give each task like its own priority level. And you just use the nested interrupt system for that. Fun fact, typically FreeRTOS runs at the lowest priority level, such that if there's any other hardware interrupts, they will jump over to that rather than having FreeRTOS run over them. Because there's not really a chance for FreeRTOS to stop running to allow the other lower priority tasks to run. Now let's look at another one that I have here. It's basically the same thing. We have here a some nested interrupts. This one's a little bit interesting because you have your user program running. Time equals 10. You run into your printer service routine, run through this. Then you have a higher priority service routine that comes in, runs that one. But at some point in here, or even at this point right here, t equals 25, another, actually no, in this case, higher priority task comes in, or higher priority interrupt comes in, we return, then immediately we get another higher priority interrupt. We move over to this. And then once we're done with that, so there's no other interrupts, we move back to this interrupt, finish the execution, and we move back to our main program. And my last one's another example. It's pretty similar to that. Yeah, same thing. We run through this program, execute, or like exit this one, move into this one, return back, go back down, and go back to your main program. So I said that there's two really important things about a nested vector interrupt controller. You need to have priority, and you need to have priority, and you need to have you need to be able to nest. Now I'm going to ask you guys, now that we've gone over this information, what happens if you remove the priority system? Let's say you're able to nest, but you remove the priority.
So that means there's
Oh, hold on. He rose his hand?
so everything all goes.
Hold on. Yeah, he's going.
Maybe it would take way too long for you to come back to your original program if you keep getting interrupted. Like there wouldn't be like, I guess, a structure. It would be like a queue, right? First come, first served.
Yeah. So kind of like to re-elaborate, so if anyone didn't hear that. The idea is that if you don't have a priority system, then any interrupt of any type can come in and spawn you off. So you have something like this, where let's say you have low priority interrupt doing its thing, then another low priority interrupt comes in, you start doing your thing, and then another low priority interrupt comes in, then you have another high priority item that comes in. You start running that one. Then you have another low priority. Now that higher priority is now starved to actually finish its server's routine, whilst your lower priority interrupts keep coming in front of it. And this will keep going on and on and on. Now, one of the actual issues here is not only the fact that you'll keep going, let's say you just keep getting more and more interrupts. If they're all unique, you keep spawning out further and further and further, the higher priority ones will get starved when they actually need to happen. The only one in this case that would not be starved would be NMI, because it's usually a separate system. Usually one pin that's specifically meant for when an NMI happens. And usually there's no vector that comes up. If there's no number associated with NMI, it's just, this is NMI, run this service routine. You might be able to gather some information, but you usually want to make those as quick as possible. Okay. Now, what about if you removed the ability to nest? What happened then?
Then you just
Raise your, okay, so from everyone from now on, raise your hand before you speak. I'm not gonna actually ask. Go.
So would that mean all the interrupts would be just rerunning in serial, waiting each interrupt would just wait for the previous one to finish before that could run, and then whatever it's giant queue at that point.
True. Now let's say that. Yeah, so that is one thing. That if you kept hold of the, if you kept the information from each interrupt that occurred, you could have consistent high priority. Actually, it wouldn't even be the problem like you would even have the queue. So let's assume in this particular case that you not only have the lack of nesting, but you also have the lack of storing the interrupt that you held before. Go.
So that means you just basically lose a whole bunch of interrupts.
Yeah.
That might have been.
Yes, pretty much. So you can end up just losing all that information. On top of that, if you did have the way to store, you'd have a big old queue. So, and if you had a lot of, if you had any items that are equal priority, which you can have equal priority interrupts, there would be one as long as that interrupt doesn't occur again, that will just be starving the other one. Okay. Alrighty. Let me bring up another page real quick.
When you say starving, you mean like CPU, right? Or what do you mean exactly?
Huh?
When you say starving, like
when I say starving?
Yeah.
What I mean by starving, it just means that like there was a service routine that should have ran, and then another one kind of got in the way, and now it's running, and it might not have given back, it might not have returned back to the previous one. It will, as long as there's not too many interrupts happening, and like there's time for it to go back to the end, because as long as you store the information for like which interrupts occurred, you should be able to check, this hardware should be able to check the interrupt flags and then be able to run them as they come up. If you have a priority system, you know which ones to run in order. If you don't have a priority system, then you just run whichever ones you got last, or whichever one occurs immediately.
So starving is just when a process is like, it's just getting delayed more and more, where it's like getting to a point where it might not even run, or it just gets.
Correct.
Yeah, okay.
All right. So now we're gonna go over to the interrupt vector table. I'm gonna go over like just like the kind of the data structure of it, and then Sri will go into the implementation of how to add your own ISRs into the vector table. Has Dr. Osmak talked about interrupt vector tables yet at all?
Yeah.
Yes?
We're
Okay.
done with interrupts. We're
Huh?
on to IO.
Okay, cool.
Yes, basically.
Okay, so actually I'm pretty sure that I can just skip over this then. So you guys pretty much understand exception numbers, like, or vector numbers, vectors, and so they say the ISRs and all that, and how they fit inside of memory? No.
I'm gonna just say no, because I know that he hasn't gone in detail on this.
Okay.
I know, like, Preet went over it in the other lab.
Okay. In which case, I will simply, when we go through implementation, that should probably clear some things up. If it does not, I will go into any detail you guys need. Okay. All right, Sri? You want to use your laptop? Or you want to use mine?
I'll just use.
I don't think I can use this. But anyways, I'm just going to tell them
You need
to
an HDMI
open that.
adapter?
Okay.
Yeah.
No, we're good.
It's fine. Can you open your project and then look at this file called startup.cpp?
Everyone know about startup.cpp? It's in L0.
Yeah, easiest. I mean, if you're using a Windows system, then Control-Shift-R, and then look for startup.cpp. Okay, you guys, can you look at line number 129 in startup.cpp?
Line 129?
Yeah.
Right here.
Right, what do you see there?
It's an array, the location of an array being pointed into.
Yes. So basically, that's the structure that's going to hold all your interrupt system, and then it consists of both NMI and the user interrupts. And then look at the keyword in 128. It says attribute section dot ISR vector. So basically, all the information that you see below, all the information inside the function array, it has all your interrupt system in there. And then the line 128 says this is the table that needs to be loaded onto the microcontroller flash, so that when your microcontroller gets reset, it knows what are the different interrupts that it needs to address once the actual user program starts running. And then in case of any interrupts, then this is the table it looks into to actually address those interrupts. So the first interrupt that you can see in line 133 is the ISR reset, meaning that is a non-maskable interrupt which has the highest priority. No matter which interrupt that you are currently executing, when you get a reset interrupt, that holds the highest priority, and then it's going to reset your microcontroller by addressing this interrupt. And then each of the interrupts here, so each of the interrupts here would have an address that it will go refer to, which has the ISR routine. So if you open the data sheet, actually the user manual, and then click on chapter 6. And then look at table 50. So this is the table which explains what are the different interrupts that's present on that's supported by the LPC microcontroller, and then what is the exception number that each of these interrupts have. If you look at the exception number, it starts from 16. So basically, for the LPC ARM microcontroller, 0 to 15 has been reserved to be used by the manufacturer, and it's not available to to be used. And then it starts from 16, which is your watchdog interrupt. And then similarly, you would have different interrupts for different peripherals that are connected to your microcontroller. So yeah, I mean this table actually gives you all the interrupts that the microcontroller can support. I would actually recommend you to go through this table and then try to understand all the different interrupts that your microcontroller supports. And then for your assignment, you would be actually using one of the interrupt handlers, eint3, and then get your assignment done. But we'll go over that in some time. Let's go back to your startup.cpp. Now your startup.cpp said something about section.isr vector. To actually understand why this attribute has been given, we actually need to look into another file called loader.ld. Can you guys open up loader.ld?
So it's not inside of any of the L's, it should be outside of that. So inside of like, the folder that holds all the L0, L1, and all stuff like that should be there.
Okay.
Yeah, so it's outside of those.
Okay.
It's one parent up.
Yeah. So do you see something in line number 29?
So keep
Yeah. So that says star.isr vector, meaning it's going to copy all the interrupt table that was present in your startup.cpp to this place here. So basically, if this is your flash, and say this is address 0, this is where your hyperload sits. And this is where your actual program starts to run. So at the beginning of this address is where it's going to copy the ISR vector table. Yeah. So your manufacturer bootloader will sit somewhere in the memory, and then the first time you load your microcontroller, the hyperload bootloader is what takes the program from your laptop to the microcontroller, and then it starts loading from the address 64K. That's what the comment in loader.ld says. So the first thing that it tries to load up is where your interrupt service routine is.
So is this file being read by hyperloader? Is that what this is for?
No, not exactly. So the hyperload, oh, wanna go?
Go ahead.
So hyperload just looks when it, so the manufacturer's bootloader runs, then it'll jump to basically our user code. So hyperload's kind of considered to be a part of our user code. When we go into our user code, hyperload basically negotiates with any serial device connected. So it'll spit out the FF that you normally see on your serial. And it says, hey, if anyone sees this FF, I want to see back like I think a 5.5. If it gets back at 5.5, that's how it knows, okay, I'm supposed to be set up to start loading. And then it'll send back some other things to do some handshaking. Once everything's kind of established, it will then start, when you start reading in data from serial, it starts dumping it into flash. It starts writing your file. But usually a good 64K in. If it sends out an FF and doesn't get anything back, whereas that's usually when you see all the LEDs light up, doesn't get anything back, then it jumps to your application, and then that's when everything else here runs. So this part is all after that. Nothing that you really can touch inside of the code that we write here has anything to do with hyperload. That's just another program. Yes?
If that's the case, then how come we can flash our board whenever we want? So I thought it's just, so it has to go through the hyperload code, then it goes into our code, right?
Yes.
So it just keeps going back into where the hyperload, it just keeps loading the hyperload code.
Every time you reboot?
Not even when you reboot, just when it runs, because we can flash the board whenever we want.
Mhm.
So even if we are currently running like a task somewhere, we
Mhm.
can flash the code in there,
Mhm.
even though,
Yeah, so it actually happens if you look at the diagram,
yeah.
and if you actually look at some of my source code for like the Python hyperloader, there's a pin, there's a couple of pins, there's a couple of control flow pins for the USB controller, the USB to serial controller. It is DTR, which I think stands for data transmit ready, and then RTS, which is like ready to send. I forget exactly what they mean, but you can still use them as general purpose I/O. So what we actually did was we set up the RTS to connect up to the NMI, which we can then use to trigger that. And we also set up the DTR to connect up to the reset. So anytime you try to do hyperload, it does a hard reset on the chip. And then that'll force it to do its manufacturer bootloader, jumps over to hyperload, runs it. That's when we read in the FF. That's when we send back our handshaking, our other byte back. We handshake a little bit, and then once we're done, we load everything else in. So it's not always waiting there, it's not always running. It's just when we reset the device, then it goes over to hyperload. So that should answer your question.
So you guys use the interrupts that way?
Yes. And yeah, actually, so another thing to put in, this was preloaded before you bought your board. So when it was manufactured, we preloaded that in. So everyone has a bootloader once they're ready. Otherwise, we have to use some other software called Flash Magic, which is a lot slower.
Right, so let's go back to startup.cpp. Now the array that you look at, starting from 150 is all your software or the user interrupts. This is where you can actually set up what kind of interrupt you want to, and this is one of the way to actually address your interrupt. So if you want to write an interrupt that needs to be addressed, the first way, there are three ways to actually address the interrupt. The first way is to hack up this function and then put your interrupt there, your function, interrupt function name there, which is going to be addressed whenever it gets to it. That's the first way of doing things. And the second way of doing it is, there is a function called ISR_register. Now, this is a function which actually looks at a predefined array where you say what kind of interrupt needs to be addressed with what ISR routine. So if you want to write your own interrupt, you can call this function and then register your interrupt with a ISR call or a function call. So that what happens then is, it's going to take your interrupt and then keep it in the queue, and then whenever it addresses or whenever there is an interrupt that is matching your registered interrupt, it's going to address that. And this is the second way of doing things. And third way of doing an interrupt is what is called the compiler trick. Where you actually tell the compiler that for one of the interrupt routines, I'm going to be defining how exactly it needs to work so that it will override whatever the system has defined it earlier. So to actually understand this more, can you open up startup.cpp again? And then look at line 66. Starting from 66 to 100. Now all these are the interrupt handlers, and then they have been defined with a keyword called alias, and then the meaning of alias is actually in line 54. What it's saying is, it's a weak function, meaning the system can refer to this function, but then if a user uses the same function name in one of his source code, then it's gonna override it with that function rather than using the system defined function. That's what it actually means. So you can use the same function name, which is, for example, timer 0 underscore IRQ handler in 67, and then you can define a function inside your source code and then write exactly what needs to be done in case a timer 0 interrupt happens. What will happen then is, instead of doing whatever the system defined timer 0 handler is, it's going to look at your function, your implementation, and then it's going to run that interrupt, and run that routine as the interrupt. This is a compiler trick. So this is actually part of your assignment, where you will be using one of the system interrupt handlers, predefined interrupt handlers, and then you will be writing your own implementation as to what the interrupt service routine should do. Okay?
And if the weak function seems a little, like attribute weak seems a little odd, just think about it like virtual functions in C++. This is a way to do function overloading in C where that's not possible. GCC gave that extended a bit of functionality.
Yes, one other thing is, when you are writing the source code for the interrupt handler in a .c file, you can just use the handler name and then write your function definition. But then if you're using this in a C++, then you will actually need to use a keyword called extern and in the quotes C, which actually tells the compiler that treat this as a C code and do not do function name mangling. So there's something called function name mangling, where in C++ you can have different source codes with the same function names, and then C++ compiler actually mangles them in order to make sure that everything gets compiled and then only one of them runs depending on how it resolves it. So similar to that, when you write the interrupt handler function in your code, since most of them are .cpp files, you will actually need to add the keyword extern C. Okay? Okay. For your lab, you will be actually looking into a file called int.c, I think so. Yeah. Basically what the implementation in that file is, it's going to look at a function handler, and then it's going to take one of the pins. It takes a function as one of the arguments, and then it takes what type of interrupt that we are trying to handle. So for example, say you have port 0.1, which is a GPIO, P2.0. If the GPIO pin needs to do something when it senses a rising edge or a falling edge, then you will say, this is the pin number, this is the edge that it needs to detect, and then this is the function, this is the ISR routine that it needs to perform. Then you will be using this, the API in this int.c to actually get the job done. That's the easy way of doing things, where you call this API with setting up, doing some init pin configuration, pin selection, and then it does the job for you. Instead, what you can do is make use of the interrupt handler, which is int3, and then write a function definition for it inside your main.cpp, before your actual task runs. You can write outside the task where you have this interrupt handler function, and then you can look at the status of the pin, and then do a certain function when the interrupt happens, and then reset the status so that the interrupt is clear. Because if the interrupt still stays the same, then it's going to trigger the handler function again and again. So it's mandatory that whenever you're done with the interrupt service routine, you clear the bits to ensure that the interrupt is reset. So the way to do this lab is you will be considering one of the pins,
Actually,
and
hold
then
on. Let me explain this part. So actually for this lab, I don't want this simply to just be where you set up a GPIO interrupt for like 1 pin or 2 pins or whatever. I want you to be able to handle any and all pins on port 0 or port 2. The reason why I want you guys to do this is because I want you guys to be a little more clever about how you guys design your firmware. Design a structure that can make your life a lot easier. I wrote the handler that will assign a particular either rising or falling edge interrupt to a particular pin in about 6 lines. The other alternative is to just use a big old list of if statements for all 64 pins. Obviously that might be a little ridiculous, correct? So the idea behind this is to write your own interrupts controller class, and to actually be able to take in any arbitrary port, either 0 or 2, you don't have to handle those two, pin number, making sure that it's valid, and then a function call basically, and then assign that to a particular pin. Okay? I'll make sure I have this listed out because that's what I want you guys to do for my class. Ways to get around this is, like I said before, that entire list of things that I put in the last discussion for, I think, SPI, like the extra things that I went over for my SPI lab. I want you guys to kind of look at that and try to use those same things for this lab. You don't really need to use unions, but you're going to be using structs. You're probably going to be using function pointers. You're probably going to need to remember how to use pointers appropriately, and not just simple like one-way pointers, maybe even double pointers. Okay. So you should be able to attach a interrupt to any particular pin, and on top of that, you need to run some service routine. Basically, if some switch happens, you can run a callback. If another switch happens, you can run another callback. I would actually suggest, and it actually states inside of the lab, that you cannot use printf inside of a service routine. If you want to use printf, you can use these use0 debug printf. But the best thing actually for you guys would actually not to actually use the printf, but actually to let's see if this is actually correct now. To actually have either a global variable, which can be thread unsafe, or to use a vtask trigger from, or like a vtask semaphore take or give from ISR. So use the FreeRTask APIs to send triggers to other tasks to do something when something occurs. So basically, when an interrupt occurs, run your callback, but try not to put any printfs or polling. Don't try to pull in it. If your interrupt occurs for too long, and another interrupt comes in as well, you can end up resulting in your code crashing. So we want your interrupts to be as concise and as small as possible. Are there any questions about the lab? What are your questions?
So, I'm not totally clear on the callback function and how that actually gets called.
How it gets called?
Yeah.
Okay.
Because I know, like, you have your service routine, but how does that?
So you
how
have
does
your
the CPU know to go to that, or like how does that connect with the vector table and stuff like that?
So for your vector table, I don't think we went over this. Let me scroll on this guy real quick. Where's my mouse? Here we are. Where are we? We are looking for eint. I believe it's eint3.
Yeah.
And I believe eint3 handles port 0 and port 2. I could be wrong on that. I think it might also be like the two separately. The thing is, I think actually no, EN3 is the one that handles port 0 and port 2. When this service routine happens, you have to check a register to see which pin is the one that triggered. So you have one ISR, and then you have your information, you have a register to tell you which pin actually got triggered. And I believe you can also find out which, like what state, like how it got triggered. Not super important though, how it got triggered, just like that it did get triggered. So you can check to see which particular pin got triggered by looking at the interrupt status register. Run that service routine based off of which number you got. Like for example, let's say you had, I'm not gonna use linked list because that's, in this case you won't want to use linked list. Let's say you had like this array. And you find that, okay, for a certain, let's say that you had like pin 5 of port 2 got executed. And you discover that, you know, when you're searching through this entire register to find which bit has been set, you find that it was port 5. It was the one that got triggered. You would then search through your structure for that particular service routine, and then you would execute that service routine. But you had to have stored that inside some data structure somewhere else. So you'd have one service routine somewhere, and then you would have one service routine somewhere, and then you have your data bank of all like the registered IOs and what type of functions they can run.
Okay. So you like just check the status register for which pin got set, and then whatever pin that was is going to reference the data structure with the function that you want to attach to that pin.
Yes. It's like coming up with a interrupt vector table for the entire GPIOs effectively. That's effectively what you're creating.
Okay.
In this case, we can only, or the hardware interrupt vector table only has for like, enough to handle like, all GPIO, that there exists some interrupt in the GPIOs inside the GPIO peripheral.
So basically, when that function that's tied to that pin is found, does the pointer to that function get like exchanged in here where that alias was or whatever?
Oh no. So you would define your function somewhere else. So let's say you wanted to do like number 3 for a register interrupt, which is weak function overload. You would then write your interrupt service routine like some function somewhere else in your code, just anywhere else. You just define it as void en3. This is case sensitive, so make sure the case is correct. Parentheses void, and then you write your service routine there. And then whatever structure, database, or whatever you have that where you can retrieve or you can scan, you can like retrieve which function corresponds with what's pinned, would happen inside of this service routine. So for any
so
and
the
all
handler, so the handler should be the one that finds that function, right?
Yes.
Okay. And then the pointer to that function should be going to where that callback function is actually defined.
Yeah, you have to store that function pointer somewhere, and then this guy will execute that function if it sees that particular bit has been set or that particular interrupt has occurred.
So that would be something that we would maybe put in our external interrupt 3 class.
Yes.
And then this handler should be external to that class, right?
It could be, but actually I would actually highly suggest that you use this method here. Using the ISR function. So there's the ISR_register that's inside of the startup page. You can use that to just give it any arbitrary function for that particular interrupt service routine. It's more dynamic. I actually think that changing the hardware interrupt vector table is actually the worst way to go about this because you can mangle up your startup.cpp. You might as well just, you pretty much should not touch it. You can do the weak function overload. There's no problem to that, but one cool thing about having the ISR register function is the fact that if you wanted to, on the fly, you could swap out the interrupt service routines if you wanted to. You have a little more flexibility with the ISR register function. So I usually suggest using that. Just give it any arbitrary function, that will become a service routine at that point. Any other questions?
So when I read through, I found that external interrupt is only identified on, or external interrupt 3 is only identified on one of the pins for port 2.
One of the pins.
Yeah, so on, you know how you determine what the function is on a certain GPIO pin?
Mm-hmm.
I only found external interrupt 3 on one of those pins in port 2.
That's
And
interesting.
I looked through on port 0 and I didn't find external interrupt 3 in there. So is it like internally attached or?
No,
or is
no.
that-
Any.
How does that work?
How does that work?
What's like the hardware
Um.
setup? Cause like I was trying to visualize it, like how it's happening in the hardware, and it just
I can simply
it's
say.
not clear. Like
So, I'm gonna go with a really quick diagram. It's not the exact diagram, but here's a really easy way. I probably can't see over here. Erase this real quick. It's a simple implementation. You have your pin. You have some edge detector. This can also be cleared, so you can have like a clear pin here. This would be some edge detector for that particular thing. And then it goes into a big OR statement. That's just pretty much the interrupt 3 flag to say, hey, system, we have an interrupt 3, we have an external interrupt 3 condition. And it just takes for each GPIO from 0 to 64 if you count them synchronously. You just take all those in. But no, that's effectively what should be happening. If you have any either rising or falling, depending on how you set up your interrupts, if any one of these flags, this guy will catch it, and then this service routine will happen. And I'm trying to find yeah.
So when we enable like external interrupts on one of those pins, we're essentially allowing the edge detector to say like, or we're allowing the edge detector to actually look for a signal on that pin.
So repeat that one more time.
So like when we enable an interrupt on a specific pin for a port, we're essentially enabling the edge detector such that that signal can go through to the OR gate.
Yeah, pretty much. Yeah, yep.
Okay, so even if like you have a pin set up for say, I don't know, SPI, right? Does that mean that you can also have an interrupt come in on that pin while that's being used? Or?
Technically, actually, you could set up a GPIO interrupt on a pin that's being used for something else. I've actually seen I've seen some examples where like someone had a PWM and every single time like the PWM like fell or had a rising edge when it restarted its cycle, it did something else. So even though it's an output, you're not taking it as an input, you could still trigger off of your own internal signals.
Okay,
So that is a possibility.
But for this lab, we should just be basically configuring the pin that we want to use as the interrupt as a GPIO.
Yes, yeah, it's all GPIO here. Yeah, don't worry about UR interrupts, don't worry about SPI interrupts. We're just looking at GPIO. Any other questions? Does everyone have an idea of like what already in their mind, like how the code's gonna look, how they're gonna structure certain things, how they're gonna build the class? Seem good? You guys over there seem like you totally understand how this is gonna work out? Yeah.
So when the user selects like what pin they want to use, right? What if they like? Do we have to like give them a range of options? Like say, hey, you can only choose from these ones because these are the only ones that we've configured as GPIO, or like,
No, you don't have to go that far. Or so like let's say someone says like puts in the number 35 for port 0. Obviously 35 is outside of the range of pins that you have.
Yeah.
In which case you could just ignore that if you notice it's outside of the range, and then print out a message saying interrupt or like pin is outside of range, and you used to do something like that. So just spit out some message saying like that's invalid.
Okay.
Yeah.
All right.
Yeah, go step by step. That's the only way you will be able to solve this problem.
Yeah.
So choose a pin, choose what kind of interrupt that you want to act upon for a rising edge or a falling edge, and then write a small routine that gets triggered. So if you can follow that for one pin, then you can extend that for other pins.
Absolutely. Get the minimum viable product done first, and then move on. I have a hard time finding out the connection between that, because I had my old code that used EN3. It's not up there. Cool. Yeah, I use EN3. Yes.
Can you repeat that real quick? You said choose a pin and then write an interrupt handler for it.
Right. So if you go to the GPIO chapter, what we did for lab 1 was configure a pin to set it high and set it low, right? So this time what you will be doing is, for one of the GPIO pins, you will be configuring it as input because it needs to send something, and then you will be setting up the rising edge and falling edge register to actually react to those edges. So you will be setting the registers for the rising and falling edge. Then, sorry.
I was just gonna say, basically, it's section 9.5.
Yeah.
Okay.
So once that is done, then you will be sensing something on the signal, like a rising edge or a falling edge on that pin. You can use another GPIO pin to actually do that, where you set high for 500 milliseconds and then set low for 500 milliseconds. And then once the pin goes high, you can actually trigger that, give that as a trigger to this pin, the input pin, which is going to call some other subroutine.
Okay.
Yeah.
Yeah. Start off with one pin, get that to work, move on to the rest. Interesting. Okay.
Yeah, see the interrupt, it does have the configuration for port 0 and port 2 for interrupts. But when you go up to the pin select registers and you're looking at that.
You saw the one that says like external interrupt, right?
Yeah.
Yeah, that's, so actually there's a note in, I think in chapter 6 that says like, when you have EINT3, it's shared with GPIOs. So there is a particular pin that can be EINT3, but it's also shared with all other GPIOs as well. So it kind of does a lot of different things. So it gets ordered in.
Okay.
Yeah. I'll send out a message if to give you like the right source that tells you like, so I remember seeing this before, but I can't find it right now. Why there's a correlation between like the EINT3 and all the other GPIOs, and the statement that says like, here's all GPIOs registered under this.
So I'm thinking is maybe that pin that they designate in there is probably like a dedicated EINT3.
It is,
pin.
yes, yes. But it can also be triggered by the
So
other
like
GPIO.
if everything else was being used up, like that one can't be used up by anything else but that EINT3.
Sure. Yeah.
I get,
Okay. Any other questions? Yes.
You mentioned callback before.
Yes.
I was kind of writing stuff and I kind of a little bit missed it. So were you referring to the interrupt service routine?
Yeah.
Callback?
So think of it more. Yeah. So you're gonna assign a callback or an interrupt service routine per a pin. You specify the port, the pin, the rising, falling, or both, and then you specify a interrupt service routine for that particular pin. But effectively, it's going to be like a software callback. You'll check it and you say, okay, this is the situation that we're doing. Call this function. Anything else? I'm probably going to define like a strict time in which people need to have like their demos ready, so that we don't end up waiting too long. Because I won't accept someone trying to clamor their demo. Once you come in, you need to have your demo ready. If you're not ready, by the time I come over to you, you'll just get the points that you got. I'll check to see what you have at the moment, but if you're not ready, so. Make sure you do this early. Make sure you get this entire thing fully working. If I tell you on the fly to switch to a different pin, and then you need to be able to work with that. Understood? Cool. All right, so we still have some time left. I'm going to, any last questions on the lab? Okay. I'm gonna go over telemetry. I'm gonna be going over this in the Friday lab as well. I'm also going over in 243 if you're in that class as well. I heard there were some people who had issues with their hyperload, or sorry, not hyperload, with Hercules. You can use this as a alternative.
It's you have
It should work in Windows, but it's going to take a little more work.
Yeah, that's what.
So if you install, I'm going to go over that actually right now.
How long will this take?
Yeah, I'm tired.
Hmm?
How long will this extra lecture take?
Like 5 minutes. Oh no, it's not extra. This is part of the class. Yeah.
Oh, okay.
Yeah, I'm going over this in all the classes.
Okay.
We're not going over it extra right now. I would have told you. I would have said everyone else is dismissed, and then you guys,
Okay.
and everyone wants to stay here can stay.
Okay.
Yeah. Okay. All right. So if you're using SJDev, actually, how many people in here are using the Windows setup? Raise your hand. Okay. So this will just mean this just means that it's gonna be harder for you to do this. If Hercules is working perfectly fine for you, then it doesn't really matter. If it's not, then you can use this as a serial monitor. I'm actually gonna mirror my screens real quick so I can see everything. Okay. Let's see what I have here. So if you are in SJDev Linux and you pulled the latest, you would have noticed inside of SJDev Linux firmware defaults a file called telemetry. Basically, what you can do is you can execute that file, and if you did this setup, it should have installed telemetry for you. So that's all set up for you. When you run telemetry, it'll open up a new browser tab. It'll also be running a Python server in the background. And what you can do is plug, if I have an cable. Yeah, does anyone have like the mini? Yeah, thank you. Just real quick. Thank you. All right. You can go over and press refresh devices. It should pop up with whatever devices you have connected. Locate the device that you want to use. I'm actually going to disable this for a sec. You can connect. And on this side, you'll see system booting, and see all the normal stuff you'd see from Hyperload or GTK term or whatever. From here, you can then type into the terminal to actually send in discrete commands. So if I send in help, and you press enter, you'll see help. If you put in info, it'll give you some info, and so on and so forth. If you press the up key, it'll go back to your previous history. You can choose to do carriage returns in line feeds. Most of the time, you'll just want to use new line, so just use the new line. When you are not connected, you can choose your baud rate. I have all the default typical ones you would see. You can change the frequency in which you want this thing to refresh. These are just ways to make sure your CPU is not using up too much memory or too much CPU. Usually 5 Hertz is fast enough. And reconnect. It'll restart every single time you connect it, just so you know. Now, here's the other kind of interesting part of this. This won't be as useful until you have more of a running system, but you can get information about your variables in real time by clicking on this trigger, this little checkbox here. And I have a whole bunch of different variables that will basically do their thing. Throughout my system, I have this little loop running that continuously changes them. If you go over to this side here, you press the graph checkbox, you'll see a graph for each one of them. So if I actually move my accelerometer a little bit, tilt my device, you'll see the z-axis go, move it up a little bit, move this guy, move back up. You see these guys kind of interacting. Put my finger on the temperature sensor, see the temp should go up, unless I don't have that working. It went down, that's bizarre. My hands are cold. Okay, that's the reason why. So you can see all this stuff in real time. Yes?
Can you make it go faster?
Yeah. So I can actually update 5 Hertz, or 4 and 5 Hertz. I can include a way to go at faster speeds. Honestly, it's like a couple lines. Yeah. You can update you can look at this to see any data that you're working with. This is actually a bad idea if you're trying to do device drivers, honestly. That's where debugging would actually be useful, but I haven't gotten the material to do debugging. So as soon as you get that stuff. But at least it would be useful when you're doing real-time operations. You can also set any one of these variables as well in the table area. So if I wanted to, I could set the M command count to 0. And now I've changed a variable in my firmware. So this guy goes down to 0 and it'll continue to count up. If I change any of these other ones, it won't matter because if I change it to 0, it'll go right back to where it was. Oh, never mind, it's also an incrementer. The cosine one doesn't matter because it will remember where it was before and just go right back. But you'll see that it actually should have dipped somewhere here. Oh, and you can also move back and forth in time and expand the area that you're looking at. Yes?
Where are you getting the variables from?
Oh, I wrote inside of the SJ Dev Linux. There is a there is a project. This is all my 146 stuff. Like when I was taking the class, called telemetry. So I have a project called telemetry, and in there we have our main, which I make a whole bunch. I make a task, give it a whole bunch of different variables, set them initially. I add them into the telemetry bucket, and then I change them over time. And I'm actually going to go over how you end up adding something to telemetry so you can use it with this software. Okay. Actually, honestly, just take a look at the example code, and it'll pretty much tell you. You create a telemetry component, you give it a name. You'll notice that the component name comes up here, so you have what's called a bucket. So there's one called debug, don't worry about that one. App is which another one I created, another one called sensors. This is a way to kind of distinguish or segregate between different types of values added in. We can call them all the same thing if you want to. You then can go over, and you could then say telemetry register variable, put in the pointer to the component that you want to register it into. All you have to do is put in the variable itself, and then put in telemetry, like basically the variable type. If you're curious about what types are available, you can hover over telemetry reg var, and you should be able to see, go over to the telemetry var header, and you should be able to see all of this: undefined, int, uint, char, double, float, string, binary, so on and so forth. And then as it changes, it'll be reflected in the telemetry program. What it's actually doing is it's continuously sending in a string to the LPC terminal to ask it for information. And what my program here does is actually sanitizes all that information so that you actually don't see it. But you might actually see this LPC here blink, which is just in between times when it's updating. Let's go back down to 1. So use up less CPU. And here's another thing to note. I see a lot of people using scanf. For the most part, for all these labs, you don't really need to use scanf. You can actually use the terminal as a means of like sending out commands to do certain things. So if you really want to, I'd suggest using looking up how to create terminal commands with the SJ1. You can look at the Social Edge for that. Another thing is if you have things printing out willy-nilly that aren't inside of a command for telemetry will try its best to try to filter out that stuff and filter out the message it sends, but it's not always perfect, and you'll end up getting a lot of garbage popping up on your screen. So if you're doing a printf all the time, telemetry will not function fully. So I'm trying to introduce you guys into ways of not using printfs as a means of testing everything, especially in this lab where you can't really do printfs inside of your ISR to make sure it's working or that it got called. You need to do something else, possibly making a global variable, possibly using the FreeRTOS APIs. So keep that in mind. From here, start moving away from doing printfs, start moving into using other systems to get your information. If you're a Windows user, I think I need to update the repo. Oops, wrong one. Okay, yeah, so the README doesn't currently have, like I have all the instructions on another README, I haven't pushed it yet. But it'll go through just some steps to do it in Windows, but it's a bit of a pain. You have to install Python yourself, you have to run my setup yourself, but after that it should work, kind of. You have to run all the steps yourself, basically.
Which Python are you using?
2.7. I think it should still work with 3 though. It should be cross-compatible. I will check that because I have Python 3 on here anyway. But I chose 2.7 just because of the fact that most systems are default come with that. I think Mac and Ubuntu both come default with 2.7. All right. Yeah, no, so if you're having any issues with GTK term or you don't want to use that anymore, if it's I found it kind of bothersome. If you don't want to use Hercules anymore, you can use this. But it's totally valid to use any one of the other ones. Any questions? Okay. That's pretty much that. You guys are dismissed. I think there was one individual who needed to